Hey, Brent Ritchie again. Going to work some more discrete probability distribution problems, and we're using a very specific probability distribution this time, and that's the binomial distribution, one of the most common ones. It's called binomial because there's only two outcomes, thus the binomial. And those two outcomes can be grouped into a format like yes, no, true, false, success, failure. So those type of problems fall under the binomial distribution. I'm going to work one or two of these by hand just to show you how arduous that was and how we had to do it when I was just your age, but then I will wimp out and use some technology to make my life and your life a whole lot easier, alleviate some of the arithmetic. Embrace technology. Recall, let's see, the binomial probability distribution. Finding the probability, we have a formula that looks like this. The probability in trials, X successes, so the probability of X successes in N trials is the combination of N items taken X at a time times the probability of success to the X power times the probability of failure to the N minus X power. And let me just list those things down here. N is the number of trials. X is our number of successes, and what a success will be depends on the question. When we're talking about births of a baby, sometimes the way the question reads, the success is having a girl. Sometimes it's having a boy. So it's just what we name it for that particular problem. Let's see, that's N and X. Then P is the probability of success. And Q is the probability of failure. Now, my penmanship is slipping here. The nice thing about binomial distributions, since there's only two outcomes and they have to add up to one, once you're given the probability of success, then it's easy to calculate the probability of failure because it's just one minus the probability of success. And also recall, and I don't know if you've done this yet, but from counting combinations, that when we say the combination of N items taken X at a time, that is N factorial over N minus X factorial X factorial. That counts how many possible groupings of X we can find out of a total group of N. It's a combination, which means the order does not matter. So let's see, first problem. Assume that male and female births are equally likely and that the birth of any child does not affect the probability of the gender of any other children. So that's given us really what the properties of that we need to be in place for a binomial distribution. That is, we need a probability of success and a probability of failure, just two outcomes, and we need them to be independent trials. So when one happens, when you have one child, that does not affect the gender of the following child at all. So they tend to state that over and over again in these questions, just so you know, we're being mathematically correct. Find the probability of exactly 7 boys and 10. So let me clear this out, make some room to write. We want the probability of 7 boys out of 10 children. So in this case, having a boy is considered a success. Let's label all the values we need to calculate our probability with our formula. N is the total number of trials, so that is 10 births. X is the number of successes for this problem, exactly 7. The probability of success, they say, assume the probability of having a boy and a girl are equally likely. So each one, and it's, I think nature bears that out almost exactly 0.5 for each. I think there may be a slightly higher birth rate for females. But for anyway, they told us they're the same. So for this problem, they're 0.5. So our probability is going to be the combination of 10, choose 7. So first of all, we need to know how many different groupings of 7 are there in 10 children to begin with. How many different ways? Because when we're talking about having exactly 7 boys, your first, excuse me, 7 children could be the boys and then followed by 3 girls, or you could have 3 girls first and then the 7 boys. And there's a lot of different ways to have 7 boys. So you need to first figure out how many different ways, how many different groupings of 7 are there when you have 10. So that's why this falls into this formula. And then we have the probability of success, which is 0.5, raised to the x power, which is 7. The probability of failure, 0.5, raised to the n minus x, which is 10 minus 7, the third power. When you're done writing this out, your 2 exponents here should add up to your n, your 10 there. Now I'm going to use, let me write this down because I'm going to switch over to a calculator here. We could grind it out by hand if we wanted to be real traditional. But I don't think anybody's going to fault me for not doing that. Let's see if I got my calculator open here. There she is. All right. This is a wonderful little online calculator. It's got some stat functions, and one of them is the combination. And we have 10, comma 7. So that's how it likes to see that one. Times 0.5 to the 7th power, 0.5 raised to the 7 times 0.5 raised to the 3. So here lies our probability. So the probability for having exactly 7 boys in 10 births is 0.117, or about 11.7%.